Let's do our second optimization exercise. It's kind of interesting that this exercise 2 is totally different from exercise 1, but we end up with a very similar mathematical situation. So exercise 2, a rectangular corral split into 3 pens as pictured is to be constructed from 300 feet of fencing. What dimensions will produce a corral of greatest area? So this is just a very down-to-earth problem. You have 300 feet of fencing. You want to make pens like this picture for some animals or something, and you want to get the most possible area out of it. I think totally reasonable situation, and it's not, to me, obvious what shapes would work best. And so let's go ahead and start the math here. We're going to go through our 4-step process. Step 1 is identify the function to maximize. And that can be hard to do. Here, the key is greatest area. So greatest is like a maximizing word. And we mean greatest by area, we mean the total area of the corral, including all 3 pens. So I'm going to draw a picture here. And I'm going to imagine a view from up above the pens looking straight down. So here's like the outer boundaries. And then there's those 2 fences going through the center, right? So this is a view, kind of a bird's eye view straight down. And we're going to have to give this shape some, the dimensions of this shape some names. I'll call one side X and the other side Y. Okay. And just let X and Y be the dimensions of the corral. And from the way I labeled things, there could be other ways you could choose dimensions. You could take the pieces along the side instead of the whole side Y, but I think I like doing it this way with X and Y. So the total area fenced in, the total fenced in area is easy to describe from the way I drew my picture. That's just going to be X times Y. And I can give this area a variable name, A equals XY. Whoops, going down off the bottom. And so this is our key, because we want to maximize the total area. The problem is we have an X and a Y. We want a function with just one input variable. So that's why in step 2, we now need to find a relationship between X and Y. And I'm going to redraw my same picture as up above. X, Y is this side. Think about the amount of fencing, because we know we have 300 feet is what the problem says, of fencing to work with. Well, we're going to have a fence here, 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 here. We're going to have 4 of these like vertical strips and 2 Ys going across. So we're going to have one X here, X here, X here, X here, a y at each end. So the total amount of fence, it's like I add up all the pieces. X plus x plus x plus x plus y has to equal 300 feet. That's 4x plus 2y equals 300. So that comes from the amount of fencing involved here. This equation between x and y is what I call our constraint. So that's the relationship between some of the variables that we need to find. The length of fencing, though, is not the function we want to maximize. The function we want to maximize is the area. So we're going to have to come back to that area function. So let's go head on to step 3 now. Step 3 is we have to solve the constraint for one of the two variables. Often it doesn't matter. Here I'm just going to solve for y in that equation. So I have 4x plus 2y equals 300. 2y is equal to 300 minus 4x. Y is going to be 300 minus 4x all over 2, or y is going to be 150 minus 2x. And now what I want to do in step 3 is I have to go back to my area function. So bring this down. A equals x times y. And I'm going to substitute in place of y this expression in x. Because in this problem, y is always equal to 150 minus 2x. So I have x times 150 minus 2x is the area, which I could now say is like a of x is the area function. And so we've accomplished our step 3, where we now have this quadratic function. A of x is equal to, I can distribute the x, 150x minus 2x squared. And I'm seeing that quadratic function up here. And so I'm feeling good about it at this point. Okay, step 3. Now, I'm going to copy onto another sheet of paper here. Let's see, we got a of x equals 150x minus 2x squared. Of course, that's the same thing as minus 2x squared plus 150x. So my a constant is -2. My b is 150. So I know the shape of the graph is a curving downward kind of parabola shape, because a is negative. So the vertex is a maximum in this case. So we want to find the coordinates of the vertex of this quadratic function. So step 4. Sorry, in the previous video I forgot to write step 4 at the point where I started finding the x coordinate of the vertex using that formula -b over 2a. That's -150 over 2 times -2 is -150 over -4. Now, I think that's going to be 75 halves. Or 37.5. Let's just call that 37.5 feet is going to be, again, where if, again, we got x on our horizontal axis, area on the vertical. So when the x value is set to 37.5, the area will be maximum. Now the question here is what dimensions will produce a corral of greatest area? So the x-coordinate is 37.5, but we need a value for y for the other dimension of our pen, right? We got that picture that looks like this, where we just found that x has to be set at 37.5 feet. So to find y, we need to plug into our relationship between x and y. We had y solved for. Y is 150 minus 2x. So 150 minus 2 times 37.5. There's no y's in this quadratic function picture, because when we set up our quadratic function, it only involved x in the area. The y information is kind of buried in there. So this is 150 minus 75. 150 minus 75, I think, is 75 feet is y. So the dimensions of maximum area are x equals 37.5 feet and y equals 75 feet. Now, I would have never guessed this in my wildest dreams, I think, for this problem, even if I thought of those pieces separately, because if y is 75 feet, each one of these segments is 25. So the smaller pens are like 25 feet by 37.5 feet. And often, again, sometimes you find out more than you need. They don't ask us what the maximum area is, so I'll just call this extra. The max area is A of 37.5, which is what we get when we plug in 37.5 into 150 minus 2 times 37.5 squared, and we can figure that out. I think it's going to be 2,812.5 square feet of area. But, so we know that. We just weren't asked that. That's actually the y-coordinate of the vertex. So notice here we didn't have to give them the y-coordinate of the vertex. 37.5, 2812.5, because all they wanted to know in the problem were the dimensions, the x and y dimensions of the pen of max area. So here was our area function that we got once we incorporated constraint information. And here's our solution to that problem, our second optimization problem. So the homework now should be similar to these examples I've given you. And you should be able to model your homework after these videos.